Hello and welcome to this video on EDEXCEL Topic 5, Formulae, Equations and Amounts of Substance. My name is Chris Harris and I'm from AlleryTutors.com, and basically just going to give you an overview for revision purposes mainly of Topic 5 for EDEXCEL. The slides that I'm using here, you can purchase them, you can use them for revision, you can put them on your tablet, your smartphone, etc. If you just click on the link in the description box below this video, you'll be able to get a hold of them there. So, like I say, this is for EDEXCEL, and it matches the specification as outlined in the syllabus, and you can see the specification points here for Topic 5. Okay, so let's start with the mole, and this is Avogadro's number. So the mole is just a way of measuring how much of a substance we have in chemistry, and normally we shorten it to mole. So basically, 1 mole of any substance contains 6.02 times by 10 to the 23 atoms or molecules. And we normally call this, this is also known as Avogadro's number. And yes, we give it these funny letters again. It wouldn't be chemistry without funny letters. It's given the letter L. So if you see this word here, this letter, that means Avogadro's number. So in a nutshell, 1 mole of water contains 6.02 times 10 to the 23 molecules of water. And 1 mole of iron contains 6.02 times by 10 to the 23 atoms of iron. So, pretty straightforward. Now, we can calculate the number of particles in a substance, and basically we can use it by using this formula here. So, the number of particles is relatively straightforward, really. It's Avogadro's number times by the number of moles of that substance. So, if you had 1 mole of that substance, you just have Avogadro's number. So, relatively straightforward. So here's an example. How many particles make up 0.67 moles of ammonia, which is NH3? So we take the number of particles is Avogadro's number times by the number of moles. You can see here the number of particles is 6.02 times 10 to the 23 times by 0.67, because that's the number of moles. So the number of particles is 4.03 times by 10 to the 23. And also be prepared to rearrange this formula as well. So they might obviously give you the number of particles and get you to work out the number of moles. So be prepared, that would just be number of particles divided by Avogadro's number. Okay, so let's look at the mole in a little bit more detail. And this time we're going to look at mass and MR. Okay, and the number of moles can be basically calculated from the mass and the MR, or AR, which is the atomic mass and molecular mass. So the number of moles is basically mass in grams divided by the molecular mass, or atomic mass, of the substance that we're using. So for example, calculate the number of moles of 23 grams of gold, give your answer to 2 significant figures. So the number of moles is just mass over AR, which is the atomic mass. So the number of moles is 23 divided by 197, 23 grams of gold, and the AR of gold is 197 if you look in the periodic table. So that gives us the number of moles to be 0.12, and again that's to 2 significant figures. Make sure you're aware of this, the degree of precision you have to give your answers to, because if you don't, you'll lose marks. Okay, so again, be prepared to rearrange this equation. You've got to be able to shuffle it around. It might get you to work out the MR or the mass or whatever. But look in your question. When you're doing these types of questions, look in your question, see what type of data they've given you. If you have any 2 of these, you could use this formula. And there's a great saying that I like to use, which is if in doubt, work out the moles. Because actually, as you'll see, the moles is the common denominator in all of these equations here. So if you know the moles, you can work out other things from that as well. So it's a really kind of good start, really. Okay, so let's have a look at solutions then. So the number of moles of a substance in a solution can be calculated from concentration and volume. Okay, so we're going to use both of these. So again, look, there's the number of moles again. So the number of moles is concentration, always measured in moles per decimeters cubed, times by volume, but the volume must be in decimeters cubed. Now, quite often, they give you in centimeters cubed, and you'll have to convert, but we'll look at converting units later on. Okay, like I say, so you'll be more likely to convert into centimeters cubed. We'll look at the unit bits in terms of the detail in the next slide, or the next few slides. But basically what we need to do is to divide by 1,000. So you might have seen it as concentration times volume divided by 1,000. That's if the volume is in centimeters cubed. So all we're doing is just make sure your volume is in decimeters cubed. You just divide by 1,000. Okay, so let's have a look at an example. So calculate the number of moles of 200 centimeters cubed of 0.35 moles per decimeters cubed of HCl. So the number of moles is the concentration, which is 0.35, times by the volume, which is 200. Notice that this is centimeters cubed, so we'll have to convert that. So the number of moles is 0.35 times by 200 times by 10 to the minus 3. So we do this times 10 to the minus 3 because this is effectively turning it into decimeters cubed. We're dividing it by 1,000. Okay, so the number of moles is 0.07 moles. Okay, so there it is, look, just to emphasize it. Right, so again, look in your question. If you have any two of the components in this equation, you can use it. So if you were given a moles and a concentration, you can work out a volume, for example. And obviously be prepared to rearrange this formula as well. That's going to be quite common and a basic skill that you need to know. Okay, we can also work out concentration in grams per decimeters cubed, which seems a bit strange. But look at your units that they give you. They'll tell you specifically if they want you to work out concentration in grams per decimeters cubed. All you have to do is take the mass of the substance that you have worked out and divide it by the volume. Again, look, gram per decimeters cubed. It gives you an idea. The units give you an idea of how you're going to work this out. Okay, so empirical formula. This is the simplest whole number ratio of elements in a compound. So let's have a look. A compound contains 23.3% magnesium, 30.7% sulfur, and 46.0% oxygen. What is the empirical formula of this compound? So the first thing we need to do is write out our elements involved. Magnesium, sulfur, and oxygen. So you can see we've just listed our elements. Then we need to write the percentages as masses. Now they've given us percentages, we just convert them to mass. So 23.3 grams, 30.7 grams, and 46 grams. We then divide these by the relative atomic masses to get the moles. So this is the relative atomic mass of magnesium, this is the relative atomic mass of sulfur, and that's the relative atomic mass of oxygen. So we just divide them, and then what we get is the number of moles. And you can see obviously we've got these decimals here. Then what we do is we find the smallest number, which in this case is 0.96, divide all the numbers by that number. And what we should get is a ratio. Now the ratio will either be whole, like this, in which case that's brilliant. If it's not, and it's really close to a whole number, then you can just round that number up. If it's something like 2.5 here, 2.5, then what you'd have to do is double all of them. So that would become 5, that would become 2, and that would become 2. Okay, so just make sure that you're able to obviously work out the whole number ratio. And the empirical formula in this case is MgSO3. So we've got 1 magnesium, 1 sulfur, and 3 oxygens. Okay, now one of the most important things here is being able to work out the molecular formula, because they could get you to do this. All we do is to work out the MR of the empirical formula. So we work out the molecular mass of this first. Then we divide it by the molecular mass of the molecular formula, and then we use this number to multiply all the atoms in the empirical formula. So just make sure you are able to convert from an empirical formula to a molecular formula. Obviously, they'll give you the molecular mass of the molecular formula, otherwise you'll not be able to work it out. But you can work out the molecular mass of the empirical formula. Just use your periodic table. Okay. So let's have a look at another example of where we could use empirical formula. This is basically where we're using combustion products, the masses of combustion products, to work this out. So let's say a hydrocarbon combusts completely to make 0.845 grams of carbon dioxide, 0.173 grams of water. What is the empirical formula of the hydrocarbon? Okay, so again, the first thing we need to do is to write down the headings water and carbon dioxide. Now this is slightly different to the other one we've seen because we just put elements at the top. This time we're just putting down our combustion products. Then what we do is write the masses of each molecule, just like what we did before. So these are not even percentages, so it's pretty much straight just put your numbers in as masses. And then we divide these by the relative molecular mass of each. So the relative molecular mass of carbon dioxide is 44. Relative molecular mass of water is 18. If we divide these two, we basically get the number of moles of carbon dioxide and the number of moles of water. And that's them there. Right, now this is where it gets a little bit tricky. Okay, so you can see 1 mole of carbon dioxide has 1 mole of carbon atoms in there. Okay, because we've only got 1 carbon in this 1 molecule. So the original hydrocarbon must have 0.019 moles of carbon. This is the same number of moles as there is molecule, because we've got 1 molecule of carbon dioxide produces 1 mole of carbon per molecule, then we can just say the number of moles is the same. Now for hydrogen, 1 mole of water has 2 moles of hydrogen in it. So there's 1 molecule of water, it has 2 hydrogens in there. So the original hydrocarbon must have this number of moles of water times by 2. And that will tell us how many moles of hydrogen atoms we've got. 0.0192. Okay, so the carbon in carbon dioxide and the hydrogen in water can only come from the hydrocarbon. Okay, so that's the only place where it could have come from, and that's how we can make this assumption here. So then once we've done that, we just take the number of moles of our substance, and all we do is we divide by the smallest number. So we're taking these moles here, divided by the smallest number. Both of them are 1-to-1 ratio. So the empirical formula in this case is just CH. Now it looks a bit odd. Empirical formulas normally do. Remember, they're just the simplest whole number ratio. They don't have to be. They don't look like anything you've seen before, and they don't actually really exist. This is just a ratio showing you how many carbons you have for every hydrogen. Okay, so ionic equations. Ionic equations show the ions that are formed in solution and show which particles are reacting. So normally we've got acids, bases, and salts. They form ions in solution. So here's a standard balanced equation for an acid reacting with a base. And you can see here that we've got the equation. This is the full standard equation. Okay, so you've got H2SO4, which is your sulfuric acid, potassium hydroxide, potassium sulfate is your salt, and water. Now what we're going to do is write our ionic equation underneath. Now if we split all the aqueous components, like your acids, alkalis, and salts, then we get them into H plus and SO4 2 minus. And obviously K plus, no H minuses, again K plus and SO4 2 minus. Water isn't an ion, so we just leave it as it is. We don't split that. Okay, what we have to do is cancel any ions that appear on both sides of the equation to its simplest form. So look left and right and then cancel the ones which are the same. So there they are. So we get rid of them. And what we're left with is basically our simplest ionic equation. 2H plus, 2OH minus, forming 2H2O. Obviously this can be simplified to just H plus, OH minus, H2O. So obviously we put the 2's in there, but that's just how it's worked out in this example. So the SO4 2 minus and K plus, these are called spectator ions. They don't actually get involved with the reaction. So you can see here that's why we've cancelled them out and we're just looking at the important bits, which is the neutralization. So this is the final ionic equation. The charges must balance. We've got 2 pluses and 2 negatives, and obviously that's neutral. So that's fine. It all works. Okay, so we're going to use equations to work out masses. Now we're going to see state symbols quite a lot now from now on. So you're going to see S means solid, L means liquid, G is gas, AQ is aqueous, which is basically just anything that's dissolved in water, so acids and salts, etc. So we're going to use balanced equations to work out theoretical masses of things. So this is going to be particularly useful in percentage yield calculations, which you'll see later on when we have to work out the theoretical mass. So calculating the theoretical mass from an equation. So for example, how much calcium oxide can be made when 34 grams of calcium is burnt completely in oxygen? Alright, so the first thing we need to do is write out our equation and balance it. Now, obviously the main thing is it's got to be balanced. So we're looking at calcium oxide and calcium. So the oxygen isn't really playing any role here, so we just ignore that. Okay, so what we're going to do is work out the MR and AR of the species involved, and we're going to write these as a mass in grams. Now you can see here, calcium is 40 if you look in the periodic table, but we've got 2 of them, so it times it by 2, it gets 80, so 80 grams. And then calcium oxide is 56 times 2, which is 112. Pardon for that, that's my phone going off. Is 112, and that is 112 grams. Okay, so we've got 80 grams forms 112 grams. Okay, and then what we have to do is we have to divide the calcium side by 80 to find 1 gram, and then we multiply by 34 to get 34 grams, and we do the same for the calcium side. So let's go for it. So we're going to divide by 80 to get 1 gram, and then multiply by 34 to get 34 grams. And then we're going to do exactly the same on this side. So we basically want to work out what 34 grams is worth, not 80 grams. So now we know what 34 grams of calcium is, and basically what we worked out is 80 grams produces 112 grams of calcium oxide, but we want to work out what 34 grams is. So this is just there as a method. So we divide this by 80, do exactly the same on this side, 1.4 grams. So 1 gram of calcium produces 1.4 grams of calcium oxide. So therefore 34 grams will produce 47.6 grams of calcium oxide. Okay, so you can see here, obviously that's the final answer. This is the theoretical mass. This is the maximum amount of calcium oxide we can produce. Okay, so this is what we call a theoretical mass. Okay, so we're going to use these state symbols like we've just seen before. There they are again. So state symbols can be used to show what is happening in reactions. So let's have a look at some displacement reactions. So these are reactions where we've got a more reactive element takes the place of a less reactive element in a compound. So, for example, F2 plus sodium bromide, or NaBr, will form NaF and Br2. So fluorine is more reactive than bromine, so it displaces it. And now the fluorine sits with the sodium. Here's the ionic equation, as you can see here. So F2 plus 2Br minus will form F minus and Br2. So we've just cancelled out the sodiums because they're spectator ions like we've seen before. Okay, acid-base reactions. Again, if you look here, these are all aqueous. Okay, so it's a displacement reaction if you look at the state symbols. Acid-base reactions. So an acid and a base will form a salt and water. Carbonates will produce carbon dioxide as well. So let's have a look. So here it is here, nitric acid plus potassium hydroxide. That'll form potassium nitrate and water. Again, this is your salt. Get rid of them spectator ions, that's your potassiums and your nitrates, and we're left with H plus and OH minus forming water. Notice the state symbols. Water's liquid, your ions are always aqueous. Here's another example. This is sulfate reacting with a carbonate. Now you can see here the additional bit. Again, here it is, potassium sulfate. So we're forming sulfuric acid plus potassium carbonate will form potassium sulfate. So we've just got a swap here. There's your salt plus water plus carbon dioxide. So all carbonates will produce carbon dioxide. The ionic equation, again, the bits which are changing, the sulfate is remaining the same, so the sulfate's remaining the same, and the potassium is as well, so we can cancel them out. And what we're left with is 2H plus, this has come from the sulfuric acid, carbonate ion has come from potassium carbonate, forms water and carbon dioxide. So you can see all we're doing is looking for things which don't change. Okay, precipitation reactions, again, when a solid is produced after two aqueous reactants react, is called a precipitation reaction. So precipitate is just a solid that is formed. So again, you're looking at these state symbols here. Barium chloride reacting with potassium sulfate. This will produce potassium chloride. That's an aqueous, that's dissolved in water. But look, this is a solid. That is a precipitate. So your precipitate that forms in this reaction is barium sulfate because it says solid on there. Okay, notice just come back here, obviously carbon dioxide is a gas, so you should see bubbling in this reaction. Okay, so barium sulfate is there, that's barium sulfate like I say. This is the ionic equation again, knock out them potassiums. We don't need the potassium bit because they're just spectator ions. And the chloride bit again doesn't change, Cl minus there and Cl minus there, so that doesn't change. So what we're left with is Ba2 plus SO42 minus forms barium sulfate. Again, that's your solid. Okay, so let's look at the mole gas calculations. So gases occupy the same volume of space under the same conditions. Now, remember we'd seen in the previous slides how to work out the relationship between moles and mass and moles and concentration for solutions. This is the one for gas. So you can see here the number of moles is the volume in decimeters cubed divided by the molar gas volume. So basically this is just the volume of a mole of gas, and basically this occupies and what this gas occupies. This is measured in decimeters cubed per mole. Okay, it's the molar gas volume. Okay, so let's say it's standard room temperature and pressure. It's basically 293 Kelvin, 101.3 kilopascals. We've got 1 mole of any gas occupies 24 dm3 mole to the minus 1. That's your molar gas volume. Okay, so this is at room temperature. At standard temperature though and pressure, which is 273 Kelvin and 101.3 kilopascals, it's actually only 22.4 dm cubed mole to the minus 1. So make sure you're aware of these numbers and you know this one's at standard room temperature, this one's standard temperature. Okay, make sure you don't get the two mixed up. So let's have an example. Calculate the number of moles of gas with a volume of 7.8 decimeters cubed at standard room temperature and pressure. Okay, dead easy. All we do is take the number of moles, which is, we work out the number of moles, which is the volume, 7.8 decimeters cubed. Okay, because that's what we've been seeing there. Divided by, because this is standard room temperature, it's 24 dm cubed mole to the minus 1, so it goes 24 there. And that equals the number of moles to be 0.325 moles. Okay, and basically we can find the volume of a gas experimentally. We can collect it in a gas syringe. We can obviously work that out if we were doing it as a practical. Or we can use one of them inverted, upturned measuring cylinders full of water and measure the volume of gas there. Okay, so gas volumes can be worked out using molar and volume calculations. Okay, so you can see here, here's a molar calculation here. So for example, how much gas in centimeters cubed is produced when 6.2 grams of magnesium reacts with hydrochloric acid at room temperature and pressure. Okay, so that's important because we're going to be using 24.3 here. Here's the equation here. Magnesium plus HCl forms magnesium chloride and hydrogen. So that's your salt and that's hydrogen gas. So what we have to do is work out the relative atomic mass of magnesium first. It's 24.3, so use the periodic table for that. And so the moles of magnesium is going to be mass over the relative atomic mass. Okay, so this is working out the moles. So the moles is 6.2 grams divided by the relative atomic mass is 24.3. That's the relative atomic mass of magnesium. And that's going to give us the number of moles to be 0.255 moles. Okay, we need to work out the moles of something here because that will allow us to work out the number of moles of hydrogen. Okay, so this is a 1-to-1 ratio. It's a 1-to-1 reaction. So the number of moles of hydrogen is also 0.255 moles. So once we know the moles of gas, then we can work out its volume. And so its volume is basically the number of moles times by the molar gas volume. We've just rearranged the equation we've seen before. So that's 0.255 times by 24. Okay, remember that was your, this is at room temperature and pressure. Gets you 6.12. Then remember that's in decimeters cubed. Or if we had to get that in centimeters cubed, we just multiply it by 1,000 and we get 6,120 centimeters cubed of gas is produced. Okay, we could also do a volume calculation as well. So for example, calculate the total amount of gas produced when 5.6 decimeters cubed, so we've been given a volume this time, of nitrous oxide N2O decomposes. So N2O produces N2 plus half oxygen, so half O2. Okay, so 1 mole of N2O produces 1 mole of N2. You can see here it's a 1-to-1 ratio. And half a mole of oxygen, so because we've got half O2. So if we had 1.5 moles of gases produced overall, you can see here that we've got 1 here and 1.5 here. Remember, we want to work out the total amount of gas produced, so we need to take into account both of them. So we've got 1.5 moles produced. So 5.6 decimeters cubed of N2O produces 1.5 times by 5.6, which is obviously your volume in decimeters cubed, and basically you'll get a total volume of gas produced of 8.4 decimeters cubed. Again, multiply by 1,000 to get it into centimeters cubed. So this is basically just a way of working out, but just watch out for things like total amount of gas produced. Okay, ideal gas equation. Now, this is fine, but obviously these are restricted, the gas equations that we looked at before, because it's assuming room temperature and pressure, but gases behave differently at different temperatures, so we need an equation that takes into account varying temperatures. So we call this an ideal gas equation. Basically, this is the number of moles in a specific or specified volume of a gas. So we use this equation here, PV equals nRT. P is pressure in pascals, and now these are standard units, so you must use these units. Volume is in meters cubed. N is the number of moles. R is a gas constant, 8.31 joules per Kelvin per mole. And T is temperature, again measured in Kelvin. Make sure it's in Kelvin. You must use these standard units. If they've given you units that's other than this, you need to convert to these units. Okay, so let's have a look at an example. So calculate the volume in centimeters cubed of 0.36 moles of a gas at 100 kilopascals and 298 Kelvin. So PV equals nRT. We've got to rearrange this. This will give V equals nRT over P. Put the numbers in. So 0.36 moles, 8.31 is the ideal gas constant. You'll get this in the exam. 298 Kelvin, because that's the temperature that we're using. Divide it by, now because they've just given us it in kilopascals, we convert that to pascals. So we times it by 1,000, so it's divided by 100,000. That gives a volume of 8.91 times by 10 to the minus 3 meters cubed. So that's your volume. So the volume, obviously in centimeters cubed, now again we're going from meters cubed to centimeters cubed. We have to times by 1,000,000. Now you'll see a conversion chart later on. I'll show you why we multiply it by 1,000,000. So we're taking the volume in meters cubed, turning it in centimeters cubed, which is 8910 centimeters cubed. Okay, so we'll have a look at the converting units later on. Okay, so important, when using the ideal gas equation, you should use the units above that have been mentioned. Make sure you can rearrange the formula properly. The gas constant will be given to you, which is 8.31, and the standard conditions are 298 Kelvin and 100 kilopascals. Okay, so you must remember that. Okay, so let's have a look at these converting units. Now you can see here I've got different dimensions here. This is one dimension. So if I'm going to meters to decimeters, because there's 10 decimeters in a meter, effectively it's just 10 centimeters, we multiply by 10. And we multiply by 10 to get to centimeters as well. Okay, so again, 10 decimeters in a meter, 10 centimeters in a decimeter, and 100 centimeters in a meter. So as you can see on there. Now, if we're going from meters to centimeters, all we do is multiply by 100 because we've got 100 of them in there. Now, for every dimension, we're going to add a 0 from the previous dimension. See here, now we're going into a 2-dimension. This is an area. So we're going to have a look at how we convert these. So again, from meters squared to decimeters squared, you can see we only had 1 0 on there. We've added another dimension. This is squared now, so we add another 0 onto there. So it's times by 100 times by 100. So again, we've added that extra dimension. Overall, going from meters squared to centimeters squared, it's 100 times 100, which gives us 10,000. Okay, so going into the one which is the most important for chemistry, which is volume. Again, because we've added an extra dimension, we add an extra 0 onto the end of there, so that's now multiplied by 1,000, as you can see. So going from meters cubed to decimeters cubed, multiply by 1,000, and go from decimeters cubed to centimeters cubed, multiply by 1,000. But if we're going from meters cubed to centimeters cubed, like we've seen before, then all we have to do, as you can see, we've added the extra unit on there, is we times them 2 thousands together, and we get times by 1,000,000, and that's why we multiply by 1,000,000. Obviously, if we're going backwards, you just divide by the same number, so the numbers don't change, but you're just dividing instead. Okay, so we're going to use equations to work out the volumes of gases. Okay, so balanced equations can be used to work out the volume of gases. So if we have a look, we're going to calculate the volume of gas from this equation here. So we're going to say what volume of hydrogen is produced when 12 grams of potassium reacts with water at 100 kilopascals of pressure and 298 Kelvin. And the gas constant is 8.31 joules per Kelvin per mole. So the first thing we need to do is write out an equation and balance it. So you can see here, there's the equation, potassium reacting with water to form potassium hydroxide and obviously hydrogen. So this is quite explosive, this. You put this in water, you'll soon know about it. You wouldn't stand near it, put it that way. Right, the second thing, we need to work out the number of moles of potassium, because we can. Okay, we've got a mass and we work out the AR of potassium. So moles is mass over AR. Remember that saying, if in doubt, work out the moles. So that's what we're doing. So working out the number of moles, 12 grams divided by 39, that gives us the number of moles of potassium to be 0.31 moles of potassium. Then we're going to use the equation to find out the molar ratio of potassium and hydrogen. So we've got 2 moles of potassium react to produce 1 mole of hydrogen, as you can see here. So the moles of hydrogen is basically 0.31, which is the number of moles of potassium, divided by 2, because it's 2-to-1 ratio. So we've got 0.155 moles of hydrogen gas. Now remember, we're wanting to work out a volume, so we're going to use PV equals nRT to basically work out the volume, because we know the moles of hydrogen. So V equals nRT over P, we've rearranged. So V equals number of moles, which is 0.155, times by 8.31, that's your gas constant. 298 is your temperature, 298 Kelvin, divided by 100,000. Remember, the pressure is at 100 kilopascals. We have to convert that to pascals, that's the standard units. So that's going to be 100,000 pascals. So the volume is 3.84 times by 10 to the minus 3. Remember, it's in meters cubed because that's the standard unit for ideal gas. Okay, so let's have a look at some risks and hazards. Obviously, a lot of this is practical based. There's a lot of practical involved here. So the hazards, basically these are things that could cause harm to you or others around you. Risks is basically the likelihood of the hazard causing harm to you or something else. Okay, so it's the likelihood of something happening. So risks in experiments can range from things like scalding from hot liquids, burns from hot equipment that you might be using, like obviously Bunsen burners, burns from chemicals, acid burns for example, cuts from glass or metals, harm from poisoning from gases and chemicals, so like carbon monoxide and chlorine. These are risks. Okay, so this is the likelihood of the hazard causing harm. So what's the likelihood of being scalded, etc. Now what we do is we need to manage these risks, and we do a risk assessment. Basically we do this prior to doing a practical. We don't do it afterwards because obviously there's no point to that. We need to work out what the risks are and what can we do to try and reduce them, and if the risk, or if there is harm, then what can be done about it to try and make first aid or etc. So for example, it needs to cover the identification of all hazards. So what are the things that could cause harm, the risk associated with each hazard. So what is the risk? So for example, it could be a Bunsen burner near the edge of a bench. The risk could be burns from somebody walking by. The likelihood of something going wrong. So is it likely to go wrong or is it not? The seriousness of the risk. If it's poisonous, then that's really serious. And how to reduce the risk. Maybe use a fume cupboard, push the Bunsen away, orange flame when not in use, things like that. So these have to be done prior to the experiment being carried out. Okay, so we need to know how to make a standard solution. So standard solutions are used in titrations and they have a known concentration. So in this experiment, we will assume we know the concentration of the chemical in the burette, and this is because it's made as a standard solution. So we can titrate this standard solution against an unknown concentration in the conical flask. So we're going to titrate it into there. So standard solutions are made from solids, okay, with a known mass dissolved in water to a fixed volume in a volumetric flask. So we know the mass of the substance we've used and we know the volume of liquid or water that we've added. And we can work out obviously the concentration from this as well. And let's see how we can, obviously we'll look at the calculations to do this. But first of all, we need to know how to make a standard solution, a practical technique. Okay, so the first thing we have to do is weigh out the amount of solid precisely. Okay, so we're going to use a balance, top pan balance, and a plastic or glass weighing boat. Then we need to transfer. We're going to transfer it from the weighing boat into a beaker, wash any solid that's left behind into the beaker using deionized water. So if there's any solids left in the weighing boat, wash it out and then tip it in. You want to try and get as much of that solid that you've weighed into your solution. Then we dissolve. So then it's obviously into our beaker. We dissolve it fully using deionized water, removes any impurities, stir it to make sure the solid is fully dissolved into the solution. Then we need to transfer it into our volumetric flask. That was a really tall flask that we'd seen before. We're going to use a funnel to avoid any spillage, rinse the beaker and the glass rod. Okay, the glass rod might have some of your substance on there, and obviously the beaker will as well. Again, you're trying to get as much of that solid in there. Okay, you want to transfer most of it in. Then we fill it. We fill it using more deionized water again to the graduation lines, a fine line in the neck of the volumetric flask. Don't go above the line. You've got to be really careful. Use a pipette when you get close to that line, drop by drop. Going over that line means you've diluted your substance more than what you think you have, and that will give you inaccurate results. And then just finally we need to mix it. So we just invert the flask a few times, tip it upside down, put the lid on it, of course. We don't want the stuff going everywhere. You've just delicately made this. And basically this makes sure it's thoroughly mixed and it's pretty much ready to go. It's a bit like making cocktails, you see. Okay, so this is how you'd make a standard solution. Now, obviously, we have to be able to calculate this bit. This is the bit I was talking about before. So let's have a look. We've got what mass of solid sodium hydroxide is required to make 250 centimeters cubed of 0.75 moles per dm cubed sodium hydroxide solution. Now, obviously, technicians in schools, lab technicians and science technicians, this is what they do on a daily basis. Okay, this is natural to them. So, but just in case you needed to make this solution, then you need to know how to do it. Because obviously sodium hydroxide comes as solid pellets. And when you get it in the lab, you'll get it as sodium hydroxide solution. But somebody has to make that up. You can't just buy it in as solutions, you know. So technicians need to know about how to calculate these things. So we're going to work out the number of moles of the solution you want to make. Okay, so the first thing, we do moles equals concentration in moles per dm cubed times by volume, which is in decimeters cubed. So the number of moles is basically 0.75, okay, which is the concentration, times by the volume. Now the volume is, remember this is in centimeters cubed, 250 centimeters cubed. Because we need to convert it into decimeters cubed, then we have to put times 10 to the minus 3 on there. But basically, that just means the same as dividing by 1,000. So we convert that into decimeters cubed. And we get the number of moles of 0.1875. So that's the number of moles of the solution that we want to make. Okay, so use the number of moles from the previous step to calculate the mass. So the mass is basically the number of moles times by the relative formula mass. So moles is from here 0.1875. Okay, remember this is the concentration. This is the number of moles that we want to obviously use to get the right concentration in that volume. Times it by 40 because that's the relative molecular mass of sodium hydroxide, and we get a mass 7.5 grams. And that is how much sodium hydroxide we need to make that volume of that strength sodium hydroxide solution. So it's pretty smart. So remember, obviously that relative formula mass just shows you how to work it out there, but you can use your periodic table for that. Okay, so let's use this standard solution. Obviously, we use it in titrations. So titrations can be used to work out the concentration of an acid or an alkali. Now, we have an acid or an alkali of the burette with a known concentration in here. That is your standard solution. That's what you've just made. Now, if we titrate that against something with an unknown concentration, but a known volume, then obviously we can work these things out. So what we're going to do is add a few drops of indicator in there as well. Okay, so if we add the chemical in the burette to the conical flask till the indicator changes colour, this is known as the end point, and we need to do it drop by drop near the end point, otherwise you'll go well past the end point. You'll see one drop makes a big difference when you're near the end point. So once we've done that, we need to read how much chemical was added from the burette to neutralise the chemical in the conical flask. We always read from the bottom of the meniscus. So as you can see here, we've got a picture here. Now the volume shown here is actually 20 centimetres cubed, but not 19.8. We're not reading from the top, we're reading from the bottom of the meniscus. Very, very important. Okay, record your results 2 decimal places, and you keep repeating until you've got 2 results that are concordant. So basically that means they're 0.1 centimetres cubed of each other. That could be your rough titer at the start, that's fine, as long as you've got 2 results that are concordant with each other. Okay, and let's just have a look at some of these indicators. So obviously phenolphthalein, acid it's colourless, alkali it's pink, methyl orange, in acid it's yellow, and in alkali it's red. Okay, so let's have a look at some calculations. So titrations can be used to work out the concentration of an acid or alkali. So let's have a look at an example. 18.3 centimetres cubed of 0.25 moles per dm cubed HCl was required to neutralise 25 centimetres cubed of KOH, potassium hydroxide. So calculate the concentration of potassium hydroxide. Okay, like I say, the first thing we need to do is work out our overall equation. We've got hydrochloric acid in here in this example, potassium hydroxide in here. So here's the reaction. Write out the equation and make sure it's all balanced. In this case, it already is. Then we do the number of moles. So the number of moles is concentration in moles per dm cubed times by the volume, okay, because we want to work out the number of moles here. It's the number of moles of HCl, again, because we know the concentration and we know its volume, because it's told us that we needed 18.3 centimetres cubed. Again, convert into decimeters cubed, times by 10 to the minus 3, and because we know that, we can then work out the number of moles of acid that we've added. 4.58 times 10 to the minus 3 moles. Again, make sure you convert your units. Don't lose marks for that. Okay. Then, once we've done that, we're going to use the equation to find out the molar ratio in order to work out the number of moles of potassium hydroxide. You can see here that we've got a 1-to-1 ratio, so it's pretty straightforward. So the number of moles of HCl equals the number of moles of potassium hydroxide. So the moles of potassium hydroxide is 4.58 times by 10 to the minus 3 moles. Then once we've done that, we then rearrange that equation and we're going to work out the concentration of sodium hydroxide. We've just worked out the moles there. 4.58 times 10 to the minus 3 divided by the volume. Again, convert that into decimeters cubed. We know they had 25 centimeters cubed in here initially to start off with, times by 10 to the minus 3 to convert into, obviously, into decimeters cubed, because that's the centimeters cubed there. And that gets us 0.18 moles per decimeters cubed. That's the concentration that we've just worked out. So that is the concentration of your unknown potassium hydroxide that we didn't know, but we do now. So relatively straightforward. Okay, let's have a look at another titration. This time we're going to work out the volume of an acid or an alkali. So I've got 15.7 centimeters cubed of 0.45 moles per dm cubed of sulfuric acid was required to neutralise 0.120 moles per decimeters cubed of sodium hydroxide. So we're going to calculate the volume of sodium hydroxide being neutralised. We're going to do this in centimeters cubed. So you can see here, the first thing, again, we're going to write our equation. This time we've changed the acids a bit. So the acid is sulfuric acid and we've got sodium hydroxide in here. Write out the equation and make sure it's balanced. You can see it's balanced there. Then we're going to calculate the number of moles of sulfuric acid. Again, it's the same thing. Work out the number of moles of the thing that we know. Concentration is 0.45 times by the volume, which is 15.7. Again, convert that into decimeters cubed. That's times 10 to the minus 3. So the number of moles is 7.07 times by 10 to the minus 3 moles. Okay, make sure we convert. Very, very important. Then we're going to use the equation to find out the molar ratio in order to work out the number of moles. We call this stoichiometry. So we've got a 1:2 ratio between sulfuric acid and sodium hydroxide. So we've got basically the number of moles of sodium hydroxide is 2 times the number of moles of sulfuric acid. So that's going to be 2 lots of 7.07 times by 10 to the minus 3, because that was the number of moles of acid. That gets us the number of moles of sodium hydroxide, 0.0141. And then we're going to use that concentration equation again. So volume this time, we want to work out the volume, is moles divided by concentration. Number of moles is 0.0141 divided by the concentration, 0.120. And that gives us the volume of 0.118 decimeters cubed. So the volume in centimeters cubed is 0.118 times by 1,000. Because remember, that's the volume in decimeters cubed. So to work it out into centimeters cubed, just multiply it by 1,000. It's 118 centimeters cubed. And that's the volume. Okay, so we'll look at some errors and uncertainty. So uncertainty is the degree of error your measurements have with a piece of equipment. Okay, so how much error we have. So the uncertainty is half the smallest increment the equipment can measure in either direction. So you can see here in a burette, which is one of the most common bits of equipment you use, there's marks every 0.1 centimeters cubed. And you can read this burette to the nearest 0.05 centimeters cubed, as any reading you take wouldn't be more than 0.05 centimeters cubed out. So you can read it, you can pretty much read it to that degree of precision. So we can say that the uncertainty of the reading will have a maximum error of plus or minus 0.05 centimeters cubed. Okay, so here we can be certain of a reading of 21 centimeters cubed by plus or minus 0.05 centimeters cubed. So the true value could lie anywhere in between 20.95 centimeters cubed and 21.05 centimeters cubed. And this is the margin of error in your readings. Okay, so it's a bit like bounds. You might have done bounds in maths, which is upper and lower bounds. So basically this is just the degree of uncertainty. So if you're using more than one measurement, all you do is you add the same units. Obviously, if they've got the same units, you add them up to get the total uncertainty. So for example, a liquid is measured using a measuring cylinder, which can be measured to the nearest 10 centimeters cubed, then measured more precisely with a burette that measures out to the nearest 0.1 centimeters cubed. Work out the total uncertainty. So you can see here the uncertainty of the measuring cylinder is basically 10 divided by 2, because remember it's half. So that's 5 centimeters cubed. That's how precise we can be. And the uncertainty of the burette is 0.1, because that was the measurement we used, divided by 2 is 0.05 centimeters cubed. So the total uncertainty is basically just 5 plus 0.05 is 5.05 centimeters cubed. So every bit of equipment you use, measure the uncertainty, and you just keep adding them up. It's pretty straightforward. Obviously, to work out the uncertainty, you just divide by the smallest increments that you can read to. Okay, so percentage error then is uncertainty divided by the reading times by 100. So for example, a 50 centimeter cube measuring cylinder has an uncertainty of plus or minus 0.5 centimeters cubed. Calculate the percentage error of the burette. Okay, so the percentage error is 0.5, okay, because that was the uncertainty, divided by 50, which is the reading. So we're using the 50 centimeter cube measuring cylinder, times by 100, so the percentage error in this case is 1% error. Now, to reduce the error, we can use more precise equipment. So, for example, we can use a pipette to measure out the 50 centimeters cubed fluid rather than a measuring cylinder. So, we reduce the error by using a larger volumes of liquid as well. So, using larger amounts reduces the error. So, measuring 100 centimeters cubed of liquid in a measuring cylinder with the same precision. So, let's have a look. We're going to measure with 50 centimeters cubed. So you can see error, remember the uncertainty was 0.5 centimeters cubed. So 0.5 divided by 50, okay, because we're using 50 centimeters cubed, times by 100, the error is 1%. But look, if we use this, but we're going to measure a larger volume, see the error is reduced. Look, same uncertainty, obviously, because we're using the same equipment, but we're measuring a larger volume, so we're dividing it by 100, because the volume's bigger. Okay, so the reading that we're using times by 100, and you can see the error has dropped massively, 0.5%. So actually by increasing the volume we're measuring, we're reducing the error, the percentage error. So Systematic errors, basically these are errors that are caused every time you repeat your experiment. So for example, if your balancing is weighing 1 gram out, it might not be calibrated properly. Every time you repeat the experiment, your results will be too high by 1 gram. This is called a systematic error. Random errors, these are basically caused through estimating readings on equipment, and so they vary with each repeat. So for example, if you repeat the titration run 3 times and get the results 18.4, 18.5 and 18.3, these are caused by random errors. Okay, so we're estimating obviously when the end point is, well, kind of. Obviously we're getting different results and different readings. So repeats and working out the mean will help to reduce the effects of random error, but it won't do that with systematic errors, because obviously systematic errors, every time you repeat it, it's not going to improve your results. You're always going to be, for example, 1 gram out all the time. Okay, so let's have a look at another example. So 15 centimeters cubed of 1.15 moles per dm cubed sodium hydroxide neutralizes 34.2 centimeters cubed of HNO3, which is nitric acid. So the volume of sodium hydroxide has an uncertainty of 0.040 centimeters cubed. The volume of nitric acid has an uncertainty of 0.2 centimeters cubed. And what is the uncertainty of the concentration of sodium hydroxide? Okay, so the first thing, we need to calculate the percentage uncertainty of nitric acid. So the percentage is 0.20 divided by 34.2, because that's the volume we're using, remember, of nitric, times by 100 is 0.58% percentage uncertainty or error. And the percentage uncertainty for sodium hydroxide, again, the uncertainty is 0.040, we've just been told that, divided by 15, because we're using 15 centimeters cubed of sodium hydroxide, that's 0.27%. So the total percentage uncertainty is just adding them together. So it's 0.58% plus 0.27% gives a total of 0.85%. Okay, so then what we have to do is calculate the uncertainty of the concentration of sodium hydroxide. So all we do is we've got the concentration here, 1.15 moles per dm cubed, multiply it by the percentage uncertainty, and that will give us the margin of error, which is 0.0098 moles per decimeters cubed. So basically, the value of the concentration could be higher or lower by this amount of 1.15. So it could be 0.0098 moles per dm cubed higher than that or lower. And that's basically how you'd use it. Okay, percentage yield. So percentage yield is the actual yield divided by the theoretical yield. Remember we looked at theoretical yield last time, times by 100. So this is the amount of product produced, assuming no products are lost and all reactants react fully. So obviously we looked at that before, but if you feel free to scroll back towards the start of the video to see how we worked out theoretical yields, but I'm going to assume we know what we're doing here. So I've just put some numbers in here just to give you an example of how you would work it out. So in a reaction involving the complete combustion of calcium, 32.6 grams of calcium oxide was produced. The theoretical mass is 47.6. Obviously you'd have to work that one out. This is just a number there as an example. Calculate the percentage yield. It's dead easy. Okay, obviously you have to calculate that by yourself. Percentage yield is 32.6 grams. That's the actual yield we've made. This is the amount we should produce in theory. Again, this is just an example number, times by 100, and we should get a yield of 68.5%. So relatively straightforward, not too difficult. Okay, remember yield is never 100%. You always lose some product, or some of your reactants don't fully react, so never is 100%. Okay, atom economy, don't get these two mixed up, they sound similar. Atom economy is basically how efficient a reaction is. So atom economy is calculated by taking the molecular mass of the desired product you want to make and dividing it by the sum of molecular masses of all the reactants, and we multiply that by 100. So that gets us the percentage atom economy. So for example, iron oxide, Fe2O3, can be reduced using carbon, which is coke, to make pure iron and carbon dioxide. So calculate the atom economy in the extraction of iron. Okay, so let's have a look. So you can see here, there's our equation. Iron oxide, Fe2O3, plus 1.5 carbon will produce 2 lots of iron and 1.5 lots of carbon dioxide. So the atomic mass of the desired product, this is the iron obviously, is 2 lots of 55.8. Remember we have to multiply it by 2 because we've got 2 moles of it. So we get 111.6, and that's the mass of the desired product. And then we do the sum of all of the reactants, which is 2 times 55.8, 3 times 16, and 1.5 times 12. That's obviously carbon there. And the sum of all the molecular masses of reactants is 177.6. And so the atom economy is basically just 111.6 divided by 177.6 times by 100. So our atom economy is going to be 62.8% in this case. Now, if you are doing addition reactions and you're adding 2 chemicals to form 1 chemical, obviously it's always going to be 100% atom economy because you're only forming 1 product. So all of your atoms are going in to actually make it. Okay, so why do we bother with atom economy? So atom economy is basically, like I say, is how efficient a reaction is. But basically, companies will try to use reactions that tend towards 100% atom economy. Reasons why: atom economies mean that raw materials are used more efficiently, so it's more sustainable. So we're not producing as much waste. Like I say, there's less waste. Benefits the environment. If we're not throwing as much away or putting so much in landfill or into the atmosphere, then that's got to be better for the environment. And obviously, higher atom economy means less byproducts, so less time and money spent separating them out from the desirable product that we want. So obviously, this is pretty useful. We don't want to be spending loads of money separating waste products, and then we have to deal with them. We have to pay to dispose of them as well. So obviously, we're going to look for things which are tending towards 100% atom economy. Okay, and that's it. That's just a quick overview. Well, a quick overview. It's quite a big topic, as you can see. So this is an overview of topic 5. Like I say, it's just purely for revision. It just gives you an idea of what's in that topic. Please support this channel by subscribing to it. You get all the latest updates and the videos that we upload, etc. If you just click on the circle, what you see right now, the circle button in the middle, and you'll be able to get that. And also, these PowerPoints are great value for money. You can get them, you can use them for revision, etc. to supplement what you've got. Obviously, it won't harm you in any way. I hope it doesn't anyway. Just click on the link in the description box to be able to get hold of it. But that's it now. Bye bye.